Hi guys, and welcome to another video. In this week we're going to be talking about regression, and we are going to be learning how we can actually do that, how we can solve real regression problems using Python. So last week we looked at just some of the ideas around regression, just kind of what it is, how you might solve it in principle. This week we're going to look at some real data, some real problems, and see how we can really solve it in Python. Okay, so just as a reminder of the key maths, in a regression scenario, we typically have a problem where we have some x data and some y data. So we have some independent variables, so that's the x data, and we have some dependent variables, that's the y data. We have some historical examples, some x-y pairs, and the idea is sometime in the future we're going to get some x data and we're not going to know what the y data is, and we're going to want to predict what that new y data is given that new x data. Okay, so we have these pairs. We have so in this kind of situation here, we have n x points and we have n y points, and in the linear situation, we basically want to say, okay, I reckon that the y data is a linear function of the x data, which means it can be described by the line y equals mx plus c. So we're basically saying, I think that the ith y variable, so that could be any of these y variables, is approximately equal to some constant m times the ith x variable plus another constant c. So that is literally just saying, I think that there is a linear relationship between x and y. Okay, so for a given value of m and c, there's lots of different choices for m and c that we could potentially choose. Some are going to be better than others, and we were saying that the error on a given for a given value of m and c is going to be the actual observed value of yi, minus our prediction, which is mxi plus c. So the error for a given point is going to be yi minus mxi minus c. Now this could be positive or negative, so the idea is we're going to square that error, because it doesn't matter if we overshoot or undershoot, either way we're wrong, so we're going to square that, and that will always make it positive. If it's a negative, it'll be a negative times a negative, which will make a positive. If it's a positive, it'll be just a positive times a positive, which is a positive. So that means that if we undershoot or overshoot, it doesn't matter, it's still the same. If we undershoot by 10 or we overshoot by 10, we're still 10 wrong. So we're going to square it, and that will make it positive either way. And then what we're going to do is basically add that error up for every single data point. So you can see here we've got y1 minus mx1 minus c squared plus y2 minus mx2 minus c squared. We'll do that for every single data point, and that will basically tell us how bad or how good our estimate is for a given value of m and c. Now this is just some kind of the maths behind it. We actually don't need to worry about this a lot of the time. It's just good to be aware that that's what we're doing. In the end, we're just going to sort of plug it into a Numpy function, and it's going to find the best value of m and c for us. But it's just good to be aware of what's going on behind in the background. Okay, so we're going to start off by running these cells. So we've got these ones here. We're just going to run them. Just to explain, so here we're doing our imports, Numpy and matplotlib. They're what we're going to need. Here I'm just filtering out some warnings. So sometimes packages will give you kind of warnings about stuff. And a couple pop up here and I just want to ignore them. So I'm just going to set warnings.filter warnings ignore. Load extensions, auto reload. Well, we actually don't need that, but that means that if you're importing external scripts and you change them, it's going to basically automatically load in those changes. But actually, we can get rid of that. Numpy set print options. Sure, we're just doing this to make our Numpy arrays look more pretty when we print them. And then %matplotlib notebook. That's just to make our plots look pretty. And then here we're importing something that I've written, some external scripts. So we're doing from script or regression to import star, which means import everything. And that's basically these things here, like the make graph 1, make graph 2. Okay, so let's run this first thing here. What have we got? Right, so this is what we're doing. So we can vary m or c. So I'm just varying c there. We can vary m there. And you can see on the bottom plot, the kind of darkness represents our error. Okay, so you can see that the lowest possible error is basically going to be where this point here where it's quite dark. So you can see up, if you look at the top, that's sort of where we have very little error. Each one of these little green and red lines represents basically the difference. So that would be, you know, yi minus mxi plus c, or minus c. Cool. Okay, so how do we actually solve this in Python? How do we find the best values of m and c? Well, to do this, we're just going to create some fake data. So what am I doing here? So I'm going to create some x data first. So I'm saying we want x data that's going to be evenly spaced between a and b, and there's going to be n points between a and b. So here I'm saying x is going to start from 0, x is going to end at 10, and there's going to be 11 evenly spaced points between 0 and 10 inclusive. So let's just run that cell. Cool, so that's what we're getting. np.linspace abn gives us an array starting at 0, ending at 10, with 11 points in between. Cool, so that's going to be our x data. And yeah, you can play around with these and change it to see what happens, but now let's actually set that, so we're just basically doing that again. Cool, so now actually we've set x equals this array, so now x is this thing here. Cool. So now we're going to set some true values for the gradient and the intercept. So just as a reminder, that's the gradient, that's the intercept. So they're going to be, well, the gradient's going to be m, the intercept's going to be 8. So we're just going to set that, c equals 8, m equals 2, fine. And now we're going to say the y value is going to be mx plus c. So y is just m star x plus c. Now, what's going on exactly here is, well, we've already set x is an array, x is this thing here that goes from 0 to 10. So when we say y equals mx plus c, what really is happening is we're saying y is going to be m multiplied by this whole array. And what that means is that it's going to be m times each element. So it's going to be m times 0, m times 1, m times 2, m times 3. And then we're going to add c, which is just a number, and that's going to get added onto the whole array as well. So it's going to be m times 0 plus c. Oh, so it's 2 and 8, so it'll be 2 times 0 plus 8, 2 times 1 plus 8, 2 times 2 plus 8, etc., etc., and that's going to end up being what y is. So let's just run that, and then we're going to print x and y. Cool. So you can see here, x is 0, so it's going to be m times 0 plus, 2 times 0 plus 8, which is 8, 2 times 1 plus 8, which is 10, 2 times 2 plus 8, which is 12, and that's how we construct our y array there. Cool. So now let's just plot this. So we're going to create a new pyplot figure, plt.figure. We're going to scatter x and y and set some labels. We just look at that. Great. It's just a perfectly straight line, as you would expect. Okay, so now we're going to add some noise, because the reality is when you collect real data, you're never ever going to see something, well, almost never ever going to see something which is a perfect straight line. There's always going to be some kind of uncertainty, some kind of noise. You know, that could originate from lots of different things. I mean, you know, let's say, let's say you were measuring basically, let's do a physics experiment where you're measuring like the expansion of a piece of metal as a function of temperature. So the real physical underlying relationship is that the length should increase linearly with temperature. But the truth is, you know, you're never going to get a perfect measurement. You're always going to be a little bit out, so there's going to be some noise. Or you might be looking at a situation where actually the relationship is more complicated than a true linear relationship, and that's often the case in data science. There's just some inherent randomness, like it's not totally defined by the x variable. So you could be looking at, say, height and weight. You're never going to have a perfect straight line. There's always going to be some fluctuation. So that's what we're going to try and simulate now. And the way that we're going to do that is by adding on random noise. Now, to explain how we're going to do that, the first thing we need to understand is the normal distribution. So I'm going to run this graph 2 now. So now just forget about noise for a second. We're just going to focus purely on this idea of a normal distribution. So a normal distribution is a probability distribution, okay? And what it describes is, it looks kind of like this. So you'll often hear it called the bell curve because it looks kind of like a bell, I guess. Or the Gaussian, that's another name for it. But basically the idea is this. It has two parameters, which are mu, this little Greek symbol here, and sigma, this Greek symbol here. And mu tells you where the center of this distribution is, and sigma tells you how wide the distribution is. Okay? And what the meaning of this probability distribution is that for any two values, A and B, the probability of it falling between A and B is this area here. So let's take the example of the distribution of height of people. It could have a central value, a mean value of, say, 170 centimeters, and a width of, whatever, 10 centimeters, let's say. And then the probability of being between, whatever this might be, 150 and 160 centimeters is going to be the area under this curve. Okay. So you can have all sorts of different distributions based up with different values of mu and different values of sigma. So now the connection to the noise is that we can simulate random selection from this distribution as well. So not only does it tell you about the probability of being between two things, you can also say, all right, well, given this distribution, give me a random value that is sampled from this distribution. Okay. And that's what we're doing here. So we're setting some values of mu. So mu is going to be 0, sigma is going to be 1. And then we're going numpy.random.normal of mu and sigma. So that's going to generate us a random variable drawn from this distribution. So if I run that, okay, this time it was 2.27. I can run it again, minus 1.58, again. It just keeps giving us random numbers drawn from this distribution. Now you'll notice that roughly half of them are positive and half of them are negative. And that's because it's centered at 0 and it has a mean of 1. So you could, if we come back up here, this would be 0, and this width would be 1. So half the time it's going to be less than 0, half the time it's going to be more than 0. And because the width is 1, basically the probability of it being, so that's 1, say, that's about 2 there, it's about 3 there. So once we get out to about 3, the probability of seeing something higher than that is going to be really, really low. And it's at the same time, the probability of it being less than minus 3 is going to be really low. And if you see this, tends to be sort of around 0. We don't often see anything bigger than 3. If we waited long enough, we would. Let's see if we can do this. See if we can get one that's happy. No, I mean, I've done it loads of times and we still haven't seen one that's bigger than 3 or less than minus 3. Okay. So what we're doing here now, we are, again, setting mu equals 0 and setting sigma equals 1. But now what we're doing is actually saying, again, instead of giving me just one draw from this random distribution, give me 11 draws. So if we run this, cool. Now we have 11 numbers, and each one is drawn from this distribution. Okay, so we run that again and again. You can see it's different. So we now have an array, a NumPy array, which is 11 long, where each one of these elements is drawn from a normal distribution with mean 0 and sigma 1. Okay, so why are we doing this? Well, the idea is that we can use this array to simulate noise on our observation. So what does that mean? Well, it means this is the case, this is the perfect case, right? So this is the case of a perfect straight line. But if we add a bit of random noise with mean 0 and standard deviation 1 onto each one of these points, then it's going to start to look not like a straight line. It's going to start to look a bit more random. Well, it'll still be sort of looking like roughly a linear relationship, but it's not going to be a perfect straight line anymore. So I'm just changing the print options here just to make it look a bit more pretty. So what we're doing here, so we're going to generate some noise. It's going to have a mean of 0, and this time it's going to have a standard deviation of 2. So you can actually change that. And then it's going to have length 11, just like both of our x and y arrays. And then we're going to say the observed y is going to be our original y, which is a perfect straight line, plus this noise. And then let's just run this and see what we get. Okay, cool. So our original y went 8, 10, 12, 14, 16. We have this noise, which is a random, where each one has mean 0 and it's randomly drawn. And then we have y plus the noise, which is just this plus this, this plus this, this plus this. So it's happening to each element. And you can see now that it's a bit more random. It's still going up, but it's not going to be a perfect straight line anymore. So if we plot that, we have an issue. I think I called it y-obs, not y-observation. So not observation. Let's plot that. Great. Okay, so now you can see that it's no longer a perfect linear relationship, but there's still some kind of straight line. And this is, the type of thing you might actually see when you go out and measure some data. Cool. So exercise 3 for you is to go and try adjusting the sigma parameter. So that's the noise, so the size of the noise. So that would be this one here, the 2. And just plot this again and kind of see how changing the noise affects the shape of this line, of this data. Okay, so we've now got some data. So it's going to be x and y observed. So let's just, as a reminder, x is still that, and y observed is that. So this is like what we'd actually have if we went into the real world. We've collected this data, x is like this, and y is like this. And now we want to find out, okay, what values of m and c underlie this data? Okay, so let's just get rid of that. So we're going changing our print options again. Okay, so the way that we're going to do this is as follows. We're going to use this thing called Numpy zeros, numpy.zeros, and I'll explain how in a sec. So you should have seen this already in the Numpy video, but just as a reminder, np.zeros 10 will give us an array of zeros of length 10. And similarly, np.zeros 15 will give us an array of zeros of length 15. Cool. So create an array of zeros of length 20. I'm sure you can do that. Okay. So that's a 1D array. We can also make a 2D array. So, if that's just a line, we want to make some kind of rectangle. And the way we do that is by passing into numpy.zeros a shape parameter. Now, an important thing to note is that you can't pass in 2 different things. We want to pass in one thing, which is this, 5, 3 in this example, which is just a pair of numbers, which tells you the height and the width. So let's just run that. Cool. So it's got a height of 5, a width of 3. It's a kind of rectangular array. But just note, if we passed in 5, 3 like that, they're going to get an error. So it wants just one thing, which is the shape. Cool. And you can see when we run this one again, we also get this is now a height of 3 and a width of 5. Cool, so now the task here is to create an array with a width of 4 and height of 8. So give that a go. Cool, so now indexing a 2D array. You may have already seen this in the Numpy video, but the idea is basically this. We can talk about any individual element in this 2D array by basically kind of using a sort of slightly different coordinate system. So you might be used to talking about squares where it's like along the corridor or up the stairs. So this would be, 1, 2, 3, and this would be sort of 1, 2. So this point would be 2, 3. When we're talking about Numpy arrays, we actually start from the top left, and we also start at 0. So this is 0, 0, 0, 1, 0, 2. And this is 1, 0, 2, 0. So again, confusingly, we don't say x, y, we sort of say y, x starting from here. So yeah, it's kind of confusing, I agree, at first glance. It does make sense, there are reasons for it, which will become apparent as you do more of this stuff, but we always start with this direction, and then we talk about this direction. So 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Okay. So MP.064. Cool. It's a rectangle of height 6 and width 4. Now, if we want to set 0, 0 equal to 1, then we say A, and we do these kind of square brackets, and we can pass in a coordinate. So we're saying A 0, 0 equals 1. Now if we look at A now, cool. So A in the top left has become 1. Okay, so now if we set A 2, 0 equal to 2, we're going to get this, right? So now it's the point at 2, 0, we're setting equal to 2. And now we're setting A 2, 3 equals to 3. So we go 0, 1, 2, 0, 1, 2, 3, and that's going to be equal to 3. Okay. So the important things to remember are it starts at 0, you do the sort of depth first and then the width. So the question here is try and make the value in the bottom right of that 2D array equal to 4. Okay, so apart from setting an individual element equal to a number, we can also set an entire row or an entire column equal to a number. So we're going to make a new array here called B, which has got 5, 5. And the way that we do that is by using this colon notation. So here we're setting B, and we're setting a whole column at the 1 position equal to 1. Okay, let's just see what we get. Okay, so what have we done here? We've set an entire column equal to 1, and which column? The one at position 0, 1. Okay, we can also do the same. So here we're setting the 1th row equal to 1. So we're doing the entire row at position 1 equal to 1. Okay, cool. So now we've got the entire column at position 1 equal to 1 and the entire row at position 1 equal to 1. Okay, so I'm just going to rerun that with some different examples just to show you the point. So I've just rerun this cell, which means B has been reset to all zeros. Now I'm going to say, let's do the entire column at position 3 equal to 1. Cool. So 0, 1, 2, 3. Now this one is equal to 1. I'm going to run that again to reset it. And then I'm going to say, okay, let's say the entire column at position 0, or the 0th column, equal to 5. Cool. So hopefully that's clear how that works. I'm going to reset that now. And let's do the same for a column. So let's set column 4 equal to, I don't know, 19. Cool. Now we've got row, the 4th row, so this is row 0, 1, 2, 3, 4. The 4th row is now equal to 19. Cool. Hopefully that makes sense. Let's put that back to the way it was. That was the other one. Cool. So we can also set a row or column equal to an array as long as the sizes match. So now instead of setting, so now we're getting a new array, which is going to be 1, 2, 3, 4, 5, and we are going to set the 3rd column equal to this array B. So let's just see what we get. Okay, cool. So now B is 1, 2, 3, 4, 5, and we're saying the 3rd column, so column 0, 1, 2, 3, is equal to this array, 1, 2, 3, 4, 5. Now this only works because they're the same length. So if I tried to do 1, 2, 3, 4, 5, 6, and now set it, you're going to get an error. So it says could not broadcast input array from shape 6 into shape 5, which makes sense, right? Because it's just too big. Let's try again. And equally, if I got rid of it, again, you can't do it. Can't put a shape 4 into shape 5. So that makes sense. But these things, of course, could be anything I want. So it could be, you know, whatever. Oh, sorry, we're missing one. Great. So now, you know, you can set any array you like along this column. Cool. So your task here is to make a new array of shape 8, 4 and set the third column equal to 8, 7, 6, 5, 4, 3, 2, 1. So give that a go. So back to linear regression, right? This was just a diversion, just a quick reminder of some Numpy array stuff. So in regression, we basically want to create this matrix X, okay, in linear regression. And we'll explain exactly why in some future lessons, but for now, just trust me that this is the array that we want to make, okay? So we want to make an array that has a height which is the same height as our X data and has a width of 2. And we want to set the first column equal to all ones, and we want to set the second column equal to our X array. So that's X1, X2, X3, all the way up to Xn. Okay, so we're going to start off by creating a matrix of zeros, which we're going to call X. So X is zeros. Now remember, our array was length 11, and this is 2. So our X data and our Y data was 11. So we had 11 X data points. So that's that there, that's the height, and 2. So let's have a look at X. Cool, right? So that's now a new zeros array, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 length, height, and 2 width. Cool. Now we want to set the entire first column equal to 1. So we're saying X, the X column at position 0 is equal to 1. Now let's have a look at X again. Cool. So we've just taken this array here and we've just set the first column equal to 1. And now remember, we want to do that for the first column, and then for the second column we want to set that equal to our X data. And we can do that because the columns is the same length as our X data. So we're saying X, everything at column 1 is going to be equal to X. And now let's see X again. Cool. So remember, our X data is just numbers going from 0 to 10, evenly spaced. So now this is what our whole X matrix looks like. And now we are almost there. The only thing we need to do is we need to call this function called np.linalg.least_. The linalg bit stands for linear algebra, and lust_square stands for least square. And that's what we're doing, actually. If you remember from the first video, or actually from the top, the reason it's called least square is because we want to find the values of m and c which give the lowest value for the square of all these errors. That's kind of where it comes from. Okay. So where were we? Here. So what we're doing is in this function, and this is really key, okay? So to the least square function, we pass the matrix X, which we just created, and the Y observations. Okay? And then we take the 0th return value from this function. So you will see this again and again and again. np.linalg.least_, X, matrix, Y, observation, element 0. Okay, now what this thing actually does is it returns us two values. It returns us the best value of C and the best value of M. And we can actually unpack those into two separate values by doing best C, best M equals this thing. So let's run this. The best value of the gradient, C, is 1.85. The best value of the intercept is 8.99. And what was the original things we set? 2 and 8. So it's not too far off. And the reason that it's not, perfectly right is because there was some noise, right? So it's actually impossible to recover the original values perfectly, given that we only have noisy observations. Okay, so just really quickly here, why are we making this matrix X? Well, it's to do with linear algebra, and the idea is basically this. If we have this matrix X, we can multiply it by a vector which holds our values c and m. And then this gives us a new array, which is basically c plus mx1, c plus mx2, c plus mx3, all the way to c plus mxn. And this can basically be seen as our vector of guesses, rather. So we'll actually come on to the details of how exactly this works in the next regression video. So you don't need to worry about it too much now. But just for your curiosity, we're going to be doing something like this. Okay, so the final exercise for this notebook is to do this whole process again, but we're going to do some use some different values. So this time you can set these to whatever you like. I've just set them to m equals 5, c equals 10. We're going to create a new observed data arrays. So we're going to do 101 x points. Again, you can play with these values. You can set them to whatever you want. And then we're going to set our y data with some random noise. Again, you can set these to anything you like. This has to be 0 because we expect that our noise should be centered around the real value. But the standard deviation you can set to whatever you want. But this has to be the same length as this. Right. So now try and create that X matrix all over again. Try and do the least square fit. And then scatter your observed data and plot your best fit. And you can refer to the plotting code above if you're unsure how to do that. Okay, great. Right, so that is the end of the lesson. I hope you managed to understand it. And there should be a new lesson coming very shortly. Okay, thanks a lot.